So I'm going to use, well, really today and Wednesday, it's all about whatever it takes to be prepared for the test. So on Wednesdays, when I'll go through the practice test and its solution, and I want to use some of the time today to do a general review of here are the topics that you need to be looking at and the kinds of problems you should be prepared for. But we also have time for homework questions, so does anyone want to fire away on those? Yes?
1 second, let me get it queued up.
Okay.
It wasn't in the calculus, it was in the algebra. The way they did it was really confusing me.
Oh, okay.
It was number 6, homework 5. Compute directional derivative of the function f of x of y equals -3 xy plus 3y squared at a point.
Okay, homework 5.
Yeah, and it was like you do the partial derivative and then you compute it using that vector or the point. And it had to do with when you added it together in that overall formula, they like moved the radical from the bottom to the top and just confused.
Which problem is this?
Question 6.
Okay. Okay, it's directional derivative or wait.
Yeah, compute the directional derivative.
Okay.
And like whenever I did the example,
Mm-hmm.
and I went through it and followed it along with the problem, the answer they gave you was just strange.
Okay.
If you just want me to like pull out the algebraic part and then write on the board and solve it, that was easy.
Yeah, I'm pulling up the shown example. So this is okay. First, want to make sure that we really are talking about the same thing. So the function, of course, the numbers will be different, but so this is 13.6, number 6. Okay, 2xy minus 2y squared, and it wants the directional derivative at the point phi 5. So that's what will get plugged into any derivatives. In the direction of a vector 5 and minus 3. Actually, this is a good problem to look at, besides what you asked about, also just how these sorts of problems need to be interpreted. Okay. So the part where you had trouble was like toward the end?
Yeah, where it's like the partial derivative of x times v of x plus the partial derivative of y times v of y.
Yeah, and working all the radicals and stuff?
Yeah, like
okay.
they moved it just, yeah.
Okay, so, all right, well then let's all step through this one. So what the problem is asking for, in a nutshell, is directional derivative of u of f, where u is in a direction of this vector, but directional derivative requires a unit vector, so it would be this vector. Can't seem to write today. Divided by its magnitude. Okay. Then I want to make sure that when you guys see this kind of a problem on a test, that there's no question as to what needs to be done algebraically also. So where are we filling it down here for the magnitude?
It's a 5 squared plus 3 squared, basically.
Yeah, 5 squared plus minus 3 squared. So we get, and I'll just leave this factored out. So 5 minus 3 over the square root of 34. So that is our u. Now, formula for directional derivative is the gradient of f at the point in question. And generally these problems, they tend to ask for directional derivative at a particular point. Dot product with u. Now, the gradient will fill in up here. So df dx, df dy the gradient is what?
The partial derivative of f with respect to x.
Which is?
2y.
Mm-hmm. And that's it for with respect to x, and then with respect to y?
2x minus
2y.
2x minus 4y.
Minus 4y. Okay. Now we'll plug in the point that we're given, 5, 5. Okay, so we're going to get 10 and then minus 10. Okay. All right, so now we know exactly what we need to take a dot product of. 10 minus 10, dot product with 1 square root of 34, 5 minus 3. Okay, and we should all know by now what dot product is. You multiply corresponding components and you add them up. So, because we're going to have the square root of 34 down below, so what will we get?
50. 5 times 10, 50.
5 on top of that.
Sorry, what?
55 on top of that is the ux component. 5 over the square root of 34.
No.
Times 10,
Yeah, times
50.
Yeah, so, but also we need to take y components into account. So we have 50. What else?
30.
Plus.
Plus 30. Okay, so all told we have 80 over square root of 34. And the only thing left to do after that would be rationalizing. So is this what you were?
That's okay. You can't have radicals on the bottom below the.
Yeah. So you do 80 squared root of 34 over 34, which simplifies a little bit. Okay.
So to do that, do you just multiply it by the square root of 34 over square root of 34?
Right. That's all it is. Yeah. Okay. On a test, I don't care.
That's my question.
Yeah. I knew it was like everybody's question here.
My last plus 3.
Yeah, and that's unfortunate. And this has already come a couple times this semester. If you want to protest its call on an answer, just show me what you did. So I have given out credit in certain cases already. So, it's not something I would want you guys expending a lot of time on. Because when for these test problems, I'm naturally going to work through them from beginning to end myself, and actually, from a purely selfish point of view, it's actually easier for me to grade if you don't take the time to simplify, because if you do simplify, then that obscures your whole solution process. So if you get it wrong, it's harder for me to see where you made the mistake and give you a fair amount of partial credit. So save yourself some time working a test and me some time grading it. And then I can get it back to you faster. Grading's my least favorite part of a job, so I try to get it done really quickly. So unless there's a situation where there's a makeup involved, like you're going to take it on Friday, then I should, again, unless there's a situation with makeup where it's not properly given back yet, I would have them turn around by Monday. Okay, so any other questions about this problem, or any other problem for that matter? Yeah. Okay. Number 9
Yep,
from the same section.
that's
Okay.
the one I was being hit with.
Okay. Okay, so this one, unit vectors of direction of steepest ascent and steepest descent, and then no change. Okay. All right, so this is 13.69. number 9. So function in this case is e to the minus x squared over 4 minus y squared over 4. And the point is 3 minus 3. Okay. And just to make sure, you guys are all getting a similar problem, different numbers, is that correct?
Yes.
Okay, all right. But so direction of steepest descent. So, and if you want, you can just learn this formula for it. It's probably the best idea. So it's a gradient at the point in question. So 3 minus 3 in this case, divided by its magnitude. Okay. So because that is what causes the dot product to be maximized, because it's pointing in the same direction as the gradient. It's just a unit vector. Now, knowing that, yeah, you just negate it for descents. Okay. Now, so actually, to talk about the last part, direction in which there's no change, it's easiest if I work through these guys. So, what is the gradient? So df dx. What Eva? What?
Well, sorry.
Negative 1/2 x
1/2.
e to the
Yeah. Yeah. So it's all this times minus 2x over 4, so minus x over 2, and then it'll be a similar thing for with respect to y times minus y over 2. Okay. And now we can plug in our given point. Okay, so we're going to get minus 3/2 here and plus 3/2 here. Okay, so we have minus 3/2 e to the minus 9/2. Okay, and then plus 3/2 e to the minus 9/2. Okay, and it's a good idea when you can, if there's anything you can factor out of vectors like these, to go ahead and do that. So that would be, for instance, if I factor out a 3/2 and e to the minus 9/2, all that's left is minus 1 and 1. And one reason it's a good idea to do that is, if you look at what we have to do next, we have to normalize these vectors. But when you are normalizing a vector divided by its magnitude, you can ignore this. At least, if you factor out anything positive, like this is always positive, because it's just going to cancel out anyway. But if positive is important because you don't want a unit vector that's suddenly pointing in the opposite direction. So, so for purposes of normalizing to get steepest descent and steepest descent, you can just take this vector minus 1 and 1 and normalize that. Save yourself a bit of time. Great thing for tests. So for instance, here we'd have minus 1 and 1 over its magnitude. What is the magnitude of that? I think someone said it already. Listen. Yeah, square root of 2. Okay. I'm not going to rationalize this. Okay. So that's that vector. And then all you have to do is negate it. 1 minus 1 over square root of 2. So any questions up to this point? Now, the last thing is, okay, find a vector that points in the direction of no change. And the reason why it says a vector is because there's actually two. They're just negatives of each other. So it must be perpendicular to the directions of steepest ascent and descent. And in 2 dimensions, like this problem, the easiest way to do that is, so this is the thing to remember. Swap and negate one. Negate one of the coordinates. Doesn't matter which one. So what would be a u that would work? You can apply it to like one of these vectors here. Yeah. So you swap and then negate one of them. So it's this vector. And don't forget, it still has to be a unit vector, so it's still over square root of 2. Or where both components are negative. So these are the two options.
What do you mean by negate? Negate the sign, or
Yeah, just change the sign. So
and you have to do both swap and.
swap. Okay, this is abbreviated, but swap the two components, and then negate one of the components. Oh, but only one. Either one. So, in general, if you have alpha beta and you want a vector that is orthogonal to that, you swap and then negate. And that way, if you check the dot product, is going to be, alpha beta minus alpha beta. It's going to be 0. Right. So this is what you need to keep in mind. All right. So ascent and descent, it's always gradient over its magnitude, and then you negate that for descent. Any questions about this one? Do we have any more? Yeah.
Number 11 on homework 6.
Homework 6. Okay, so this is max and min.
I guess I don't really understand what the question's asking.
Okay.
I think I'm like thinking of
Okay, number 11. Okay. Okay, I see what you mean. All right. Because once you know, I guess as a formula, what function you're supposed to take find a max or min of, and then you just go ahead and follow the usual procedure. You take a gradient set equals 0. But in this case, that function is not explicitly given as a formula here. It's given in words. Bless you. Okay. Bless. Okay. All right. So this is homework 6, number 11. This is find the point on the plane 2x plus 5y plus z is equal to 10. Closest to, nearest the point 2, 0, 1. All right. So you want to minimize, since it's saying you want the closest point, that tells you what you're trying to minimize is a distance. So your function Okay. Fxyz is going to be so if you think of this as distance from a point 2, 0, 1, where you can start arriving at a formula is x minus 2 squared plus y minus 0 squared plus z minus 1 squared. However, that is not the function we're actually going to find a minimum of, because the minimum of this particular function, as I've written, is obvious. The distance is 0 if I just pick x, y, z to be equal to 2, 0, 1. This is where we have to take into account it's not just any point x, y, z. We have this constraint, 2x plus 5y plus z is equal to 10. Okay. Now, okay. So in fact, what you can do is, it looks like you're trying to having to solve a 3-dimensional max-min problem, but it's not true. You're actually solving a 2-dimensional max-min problem, because restricting yourself to this plane, because a plane is a 2-dimensional entity that lets you cut out z. So the way you can enforce that x, y, z must be on this plane is to take advantage of this equation in here. So you can take this equation and solve it for z. So z is 10 minus 2x minus 5y. So really, this is the arrow I should use. Plug that in for z. So now you really have a function that I'll call g of only x and y. So now you're going to apply the usual minimization procedure to that. So you're going to find where dg dx and dg dy are 0, and then find a actually, for this kind of function, generally you're going to find only one critical point, which will turn out to be the minimum. This function can't have a maximum because you can get as far away from 2, 0, 1 as you want. But by making a substitution, you're guaranteeing that whatever x and y you find, z is automatically going to be the correct one. So, yeah, it's pretty common for these minimization problems to say, find such and such point that's closest to whatever. And the thing you can take away from that is what you're minimizing, the actual formula starts with the distance formula, and then you work with that. Does that answer your question?
I think so.
Okay. All right. So this, replacing this, is now your function of x and y that you'll find a minimum of as number problems. Okay. Other problems. Homework problems. Going once.
13.6, some on 11.
13.6. Okay.
I got the slope, but it was the gradient, I suppose.
Okay.
After that.
Okay, so it's asking for, okay, use slope of tangent line. Okay, verify that the tangent line is orthogonal to the gradient at that point. Okay. Okay. Okay, so this is, we have an ellipsoid. Okay, so 1 minus x squared over 16 minus y squared over 64. And the point is minus 1/2 minus the square root of 2. Okay. And we're looking at the level curve. F of xy is equal to square root of 61, nice, not so nice number, square root of 61 over 8. Okay, so what's the slope of a tangent line at this point, and verify that the gradient of f is perpendicular to that tangent line. Okay. So what you can do is, if I define, so first for slope of a tangent line, I'm going to define a function g of xy that defines this level curve. So it's just going to be f of xy minus square root of 61 over 8. Just for uniformity, so the curve is described by the equation g of xy is equal to 0. Now, the slope of a tangent line, which as usual I'll call m, when you're dealing with an implicitly defined function like this, so that's dy dx, but for an implicitly defined function we have a formula for that, it's minus dg dx over dg dy at the point in question, x naught, y naught, x naught, y naught. Okay. All right. And of course, the alternative is you can just go ahead and, well, actually, yeah, you're going to need to compute the partial derivatives of f with respect to x and y no matter what. Okay, so any questions about this part of a problem? I know you're asking about the other part, but okay. So when you have an implicitly defined curve, something like this, function of x and y equal to 0, this is your slope of your tangent line. Now, once you have that, so like if I were to draw a picture of a situation, here's your tangent line, and you want to verify that the gradient is behaving like this. And the thing is, the gradient of f and the gradient of big G are the same because they only differ from one another by a constant. Okay, now the gradient vector, that's no problem to get. So the gradient of f at this point of tangency, x naught, y naught, that's just the partial derivatives at that point. And I assume that your difficulty is what do we use here? What do we take the dot product with? Because you want to show that the gradient dot product with this vector for a tangent line is equal to 0. But what should that vector be? So for this, use this vector. Keep in mind what is slope. rise over run. So if x changes by 1 unit, then how much does y change by? What?
1 unit? You
Well,
said-
the slope.
Slope, m units. So use the vector 1m for whatever slope you got. So to check orthogonality, check that df dx, df dy at that point, dot product with 1m, which is just going to be fx plus mfy, is equal to 0. All right, because for a tangent line, there's infinitely many vectors you could use, but they're all multiples of each other because the tangent line is going in a certain direction. But they also satisfy the property that for every 1 unit of change in x, you have m units of change in y. So as long as so you can pick any vector that's a multiple of this, but you might as well pick the simplest one and use that. All right, so we just check that dot product is equal to 0, and that's it. Any more? All right. I mean, we may well have time for more Wednesday if needed. All right. For the test. There's a number of these things we've seen already just from talking about these problems. And it's such a fundamental task for many other types of problems, but just for its own sake, first and second partial derivatives, which you've had a lot of practice computing by now. Excuse me, the thing to keep in mind, just for saving time, is the fact that mixed partial derivatives are equal. So if I give you a function like I do in a practice test and say, give me all first and second partial derivatives, there's really only 5, not 6, distinct partial derivatives to compute. Okay.
Would it be yx for one of them?
Sorry,
Instead
what?
of xy for both of them?
Sorry. Yeah. Not such a great Monday. Oh, it's true, but fxy equals fxy. You never know, what if a reflexive property goes away? Then we're all in trouble. Okay. Now, the next kind of task is finding the equation of a tangent line or plane to, or a level, like tangent line to a level curve, or tangent plane to a level surface. The procedure is very similar. So we kind of touched on this with the discussion of a last homework problem. So we have equation f of xy equals 0, or similarly, f of xy equals a constant, and you can just move it to constant to the other side. That describes a level curve. So the slope of a tangent line, m is minus fx over fy. So that would be dy dx, assuming that fy is non-zero. Or alternatively, you can say partial of f at that point times change in x plus partial of y at that point times change in y equals 0. That's a perfectly acceptable form of the equation for a tangent line. As opposed to, this is like the standard form as opposed to like slope-intercept form or point. It's pretty close to point-slope form. And similarly, for a function of 3 variables, that is a level surface. And the tangent plane would be very similar. We just have another term for z. So doing all that would give you the equation of a tangent plane. And for this kind of problem only makes sense if, in addition to a function, some point is given, x naught y naught or x naught y naught z naught. All right. Now that covers tangent lines, tangent planes for implicitly defined functions. But what if a function is described explicitly? So you don't really have a big f of x y equals 0. You instead have y equals f of x, or z equals f of x y. So what happens in that case? Now, finding a tangent line in that explicit case, that's really a Calculus 1 problem. I'm not going to give a Calculus 1 problem, a Calculus 4 test, because you guys wouldn't do well on it. I know how your memories are.
I do have a question
Yeah.
about this. You've talked about the subject before, so what is the average on the very first calculus 4 test that you normally teach? What would you say would be the
Well, last time, because the format's changed a lot. Like because I didn't always give in-class tests. I know some previous instructor before I taught the first time had given take-home tests. I thought, okay, I'll do that too. Problems were harder, of course. Actually, they were incredibly, ridiculously hard. And last time I taught was when I switched to give an in-class test like this one, and the average was actually pretty high. And that's why your test will have 6 problems instead of 5. Because I was concerned that it was maybe a bit too high relative to the level of knowledge. But the thing is, what I'm throwing on there, you saw the first problem in the practice test, compute these partial derivatives. It's not going to take you very long. So that'll slow you guys down a little bit. But I imagine, based on history and looking at the homework scores, I think the average is still going to be pretty decent. So don't let me down. No, my classes tend not to have a bloodbath for a test, if that's what you're asking. Okay. I mean, you get that everywhere else. So, okay. Okay. Although the other thing that is different from last time, I allowed people to be exempt from a final if they had a high enough average, and we're not allowed to do that sort of thing anymore, like department policy. So everybody takes a final. Sorry. Okay. So z equals f of x, y. Then the tangent plane would be z minus z naught is equal to partial respect to x times the change in x plus partial respect to y times the change in y. So you guys have to keep straight which situation is called for. Is the function described implicitly or explicitly? I'm going to use the appropriate equation for the tangent line or tangent plane. But yeah, tangent line is not worth talking about here because that's a Cal 1 problem. Actually, this takes me to the very next item, linear approximation. In fact, this is a linear approximation. There's practically nothing for me to write, but I'll give a formal definition anyway. So the linear approximation of a function f at x, y, z, and I'll write it for three variables, for two variables, and it generalizes from there, would be the function value at x naught, y naught, which is z naught. So what I'm writing here and here are essentially the exact same thing. Just slightly different notation. So still fx, change in x, plus fy, change in y. And so I would give you a problem where you compute this function first at a given point, and then use this to estimate f at a certain point, a given point that is near x naught, y naught. And in fact, what I would recommend is, it might be worth the time, because you only have to give me the estimate, but I would suggest also compute this exactly. Go ahead and take your given point and plug it, you have to plug it into the linear approximation, that's what I'm asking for, but also plug it into f. Why? Because the two should be close together. If they're like way off, then you messed up somewhere, and at least you're giving yourself a chance to catch that. Sometimes it's worth a time to do some sort of sanity check on your answer. Like for instance, certain problems where you know the answer is supposed to be positive for whatever reason, like you have to compute an integral that's a volume, and when you get a negative answer, you know you messed up. Any questions about this kind of problem? Actually, I don't have much time left. Okay. I won't be able to talk about everything now, but I can just continue this on Wednesday.
Do we need the attendance sheet?
What?
Are you taking attendance?
Oh, yes. And looks like a handful of people are not going to be happy with you, but they'll never know. They're not here.
Not at all.
Okay. Yeah, well, we seem to have our regulars that don't come.
And then after they wouldn't be regulars.
Yeah, but they're like
Regular.
negative for regular.
You're negative regulars. You're regular.
Or stuff before we say the usual suspect.
Okay. All right. So, well, actually, the only thing that hasn't come today, because the other things I'll bring up, the directional derivative and finding max min, and we've already talked about those things. So for instance, as an example, if w is equal to some given function of x, y, z, and let's suppose that x, y, and z are all given functions of two other variables, s and t. So all of these things would have to be given. Then the question would be, what is dw ds and dw dt? So the derivatives of the outermost dependent variable with respect to the innermost independent variables. And you just have a cancellation pattern. So df dx, dx ds, plus df dy, dy ds, plus df dz, dz ds. And then similarly for t, now what I'm writing here is the result of a dot product in each case. dt plus df dz, dz dt. Because I worked this out earlier using matrix multiplication, but this is the same as the gradient, the dot product with xs, ys, zs, for the first one, and this is also the gradient dot product with xt, yt, zt. If you looked at the cases that we've seen, like this, if you recognize the pattern to how the derivatives work out, then you can just go with that. The only reason I talked about products is as you can see where these pattern derivatives come from. But alternatively, you can just learn this, and that's what you write down. It's just that we have different cases depending on how many variables you have. So really, the main thing for you to do, once you see the problem, is ask yourself, what are the independent variables? What are the dependent variables? How many of these derivatives do you need to compute? So what you need to do is, for each outer output, so in this example, you only had one, it was w. You need a derivative with respect to each inner function input. In this case, s and t. The x, y, and z are the outputs of the inner function, the inputs to the outer function. Those are the intermediaries. And that's what you are canceling, effectively, in your derivatives. So that's the pattern to learn from the cases that we've seen. All right. So keep this in mind so that you're producing the answer in the correct form, a correct number of answers, because it's usually happen if I have, say, you might think, there's only one dependent variable and only one derivative. No, you need two, because you have two of these independent variables here. Okay, but we can talk more about this and other things on Wednesday. But the number of answers is how many of these you have times how many of those you have. And I just forgot to record all of that. Dang it. Okay, so there's your quick chain rule tutorial. Well, at least only 3 people were missing.
Just enough